Hello everyone, welcome to my lecture series on math and physics. My name is Timothy Nguyen, and in today's lecture we'll be discussing Stokes Theorem. So we'll assume that you've taken some multivariable calculus in this lecture, in which case you will have seen a particular Stokes Theorem, which relates contour integrals to surface integrals. And you will have also seen other similar looking theorems like Green's theorem and the Divergence Theorem, which also provide certain identities among integrals. And if you stare at these theorems, you might ask yourself if there is a common underlying thread among them. It turns out that the answer is yes, that they are all special cases of a theorem that's perhaps also confusingly known as Stokes' theorem, but not to be confused with the particular Stokes' theorem in multivariable calculus. This more general differential geometric Stokes' theorem is actually remarkably simple, and it has far-reaching implications in many other areas of mathematics. For example, it motivates the concept of cohomology. But for our purposes, we will be focusing on Stokes' theorem not only because it's a nice way to unify disparate parts of calculus, but also because it will help us to understand the concept of curvature in the next lecture. So just as a heads up, this lecture will be fairly technical, and it's not meant to introduce multivariable calculus to first-timers, but rather it's meant to provide a higher level view of calculus using the tools of differential geometry. All right, let's go. Okay, so let's start with the most basic version of Stokes' theorem, which is that of the fundamental theorem of calculus. All right, so what does the fundamental theorem of calculus state? Let's recall that. It states the following. If I compute an integral of the derivative of a function along an interval from a to b, then I can compute that in terms of the function evaluated along the boundary. So in this case, I just have f of b minus f of a. And the reason why this theorem is called the fundamental theorem of calculus is that it relates two of the most important concepts in calculus, namely the derivative and the integral. And it shows that the integral is essentially an antiderivative since it undoes integration. Another thing to focus on is that observe that the left-hand side involves the interior of the interval of integration. Right, so here's our interval. And so here's our function, 2dx of f. Right, so the integration is happening along the interior of the interval. Whereas the right-hand side is happening along the boundary. Right? We only need to evaluate the function f at the points b and a, which constitute the boundary of the interval of integration. And when we generalize to Stokes' theorem, a similar phenomenon will happen. We'll be relating what's going on the interior, what's going on the boundary. So let's state right now that what Stokes' theorem is that it's a higher dimensional generalization of the fundamental theorem of calculus. Okay? And it requires using differential forms, which we introduced in the previous lecture. Okay? In some sense, that actually justifies why we had to introduce differential forms, because that's the only way in which we can state this very useful generalization of the fundamental theorem of calculus. While we're at it, let's state some other noteworthy observations about the fundamental theorem of calculus, because it will also reappear once we state Stokes' theorem. So other things we can observe are that the left-hand side involves a derivative. Right, so the left-hand side of this equation here, whereas the right-hand side has no derivative. Another thing we can observe is that the left-hand side is really a one form. Right? So the fact that we have a dx here means that what's going on inside this integral is really a one form. The integrand is a one form. We're integrating a one form along a one-dimensional object, which is an interval. On the other hand, the right-hand side involves a differential form of 1 degree lower, a zero form, which is just a fancy name for a function. And indeed, we only have f on the right-hand side, which is indeed a function. So we will also see this when we state Stokes' theorem. It's going to involve a derivative on the left-hand side with no derivative on the right-hand side. And also it relates differential forms of general degree with differential forms of 1 degree lower. The main thing, however, that we have to introduce is what exactly is this notion of a derivative that we're going to introduce for differential forms? What is the right notion that will allow us to state this generalized fundamental theorem of calculus? Okay, so that is what's going to lead us to the notion of an exterior derivative. Okay, so the exterior derivative is the following operation. It's denoted by d, and it maps differential forms of degree, say, k, to differential forms of one higher degree. Okay, so here we're working on n-dimensional space, so that's Rn, and k is just a general integer, so that we're working with general degree k forms. So let's just recall this is degree k forms on Rn. That's what that notation means. Okay, let's unpack that. We discussed differential forms in the previous lecture, but let me just remind you what exactly this object is. So it's quite a bit of notation, but once you get used to the notation, it's not so bad to work with. So this object is just the span of a bunch of symbols, okay, these wedge products. So k means I'm going to have wedge products of k many objects. So here, recall that that we have the dx1 through dxn as our basis of one forms. And when we look at k forms, we're just going to take k distinct elements from those n and wedge them together. Okay, and we can summarize that as follows. We want these indices here, k many, to be distinct from 1 through n. And why are they distinct? Remember that if you wedge an element with itself, it's 0. And also, if you switch to wedge products, you get a minus sign. So that tells us that we can ignore repeated indices, and also that we can order them in increasing order, because any other permutation will just differ from the ordered arrangement by a minus sign. Okay? Yeah, a minus sign or a plus sign. Depends on whether you have an even or odd permutation. Okay, so let's write this span a little bit more explicitly. We can write it as just a sum over some coefficient function, which I'll denote by f sub I, and times d sub x I. Okay, so here I is just a set of indices of size k, right? I is a subset of 1 through n, and yeah, that's what I mean. And all I have to specify is what this notation dx to the I means, and it's precisely just a compact notation for these wedge products when I is just this tuple I1 through ik. Right. Okay. So that's what the set of k-forms in Rn looks like. Okay. So how are we going to define the exterior derivative? So let's just define it on one of these monomials here. Right? So here f sub I is a function. It's multiplying this coordinate k form d sub xi, what does d do, the exterior derivative? What it does is that it just differentiates this coefficient function in every possible direction, and then it wedges the corresponding one form corresponding to that direction with the k form that's already there. So in this case, it's dxi wedged, so dx little I wedged dx capital I. Okay? And recall I'm using Einstein notation here. So this I is being summed over. It's the sum over all possible directions. Okay? And what we can do is that we can extend this formula. Once we've defined it on one of these monomials, we can define it on all of k forms just by linearity. Okay, so this is pretty compact notation. Let's do an explicit example, and hopefully it should be clear what this notation means. Okay, so let's do n equals 3, and let's do all possible values of k. So k equals 0. So for k equals 0, we just are dealing with functions. And so d of a function is the following one form. I just differentiate with respect to every possible direction. And so I get the following. Okay? So there are 3 directions, 3 coordinates, x1, x2, x3. I differentiate f with respect to each of them, and I multiply by the corresponding coordinate 1 form every time I differentiate. Okay, so indeed we have a 0 form, right? This is a 0 form on the left-hand side, and this is a 1 form on the right-hand side. Okay, let's look at the case of k equals 1. So let's differentiate a 1 form where all I have is actually let's do something even more basic. Let's differentiate just one of these coordinate 1 forms, right? Where the coefficient, I could think of the coefficient here as 1 times dx1. Okay, actually let me just erase that and put it on the right-hand side. So if I use the formula above, well, the coefficient function is really just a one constant function. Okay, and so when I differentiate, I'm actually just going to get 0 because, right, I should differentiate with respect to every direction. Right, but the one function is constant, so all the derivatives vanish. And so that's why I get 0. Okay, let's do something more interesting. Let's differentiate a 1 form where I just have a dx1, but I have a general function f multiplying it. Okay, so then in this case, let's just write out the formula, right? I differentiate with respect to each direction once before and do the corresponding wedge product. Okay, what do I get? Well, dx1 wedge dx1 vanishes, and I just have the remaining 2 terms. So what I get the following. Yeah. All right, so that's what I get when I compute the exterior derivative on this particular 1 form. I get a 2 form, which is given by the right-hand side. So as we see, here's a 1 form, and here's a 2 form. Okay, and so let's compute the exterior derivative of a general 1 form. So what did I mean when I said extend linearly? So this is what a general one form looks like. It will have 3 components with 3 different coefficient functions. So I just mean just apply the exterior derivative d to each of these. Okay, and then you could just apply the corresponding formula. Okay, so it's equal to whatever it's equal to. So we already did the first term. That's this was above, right? And then the second term will look like that. Where we differentiate with respect to each component and do the corresponding wedge product. And then likewise for the third one, okay? And then we can simplify accordingly. So for example, we'll once before have a term that vanishes because any wedge product of a one form with itself is going to be 0, okay? So that's what I mean by extend linearly. Okay, and let's finish. Actually, I guess we have 2 more cases. We have the k equals 2 case. So for k equals 2, then we can, for example, look at d of something like this. Let's just choose the 2 form that has only a dx1 and dx2 component. Again, we can extend by linearity. Let's start saving some steps now that we're used to how this works. Because our differential form has these 1 and 2 components, we know that we don't have to differentiate with respect to the 1 and 2 direction, because we're going to get a dx1 wedge and a dx2 wedge, and that's going to get annihilated because we already have a dx1 and a dx2. So the only direction we have to care about is the x3 direction. And so we can just save some steps here and just write this as follows. Okay. And so what's important is that the wedging happens from left to right, right? So the dx3 happens in the front, and then you wedge everything else. And this why it becomes actually very important to be very careful with your signs. There's minus signs everywhere because as soon as you start adding things together, you might want to reorder your terms, and that's going to introduce minus signs. So in this case, for example, it's convenient to order indices in increasing order, and so we can move the 3 to the right. Actually, in this case, we don't pick up an overall minus sign because we move it to the right twice, right? So if we move it to the right once, we get this. And then if we move it to the right again, we pick up another minus sign, which cancels out the minus sign what we already have. And so that's our final answer. Okay, and as before, we have a 2 form on the left-hand side and a 3 form on the right-hand side. And finally, for the case k equals 3, so now there's only, well, one basis vector to consider, the dx1, dx2, dx3. We wedge all of them together. Well, there's nothing for d to do because there can't be any other non-trivial higher degree form, right? We have to get a 4 form, but we know that the only degree 4 differential form in dimension 3 is 0. So this has to be 0. And we can see that because any direction we differentiate f in, that wedge is going to get annihilated when it wedges with the other, with the volume form, this top degree form here, right? Because it already has every component. Okay, so this is what the exterior derivative looks like. All right, so now that we've described the exterior derivative, we can now state Stokes theorem. Okay, so what does it state? Well, suppose we're given a k-dimensional form on Rn. By the way, there's Stokes theorem generalizes to general manifolds. It's actually a statement about integration on manifolds, but for simplicity, we are focused on Rn, but everything we do can be generalized to general manifolds. Okay, so we have a K-form on Rn. We're given some domain, which is, I'll denote by omega. So omega is a K plus 1 dimensional domain. So it's some, just basically some open set. It locally looks like an open set in K plus 1 dimensional space. Okay, so that's what we mean by K plus 1 dimensional domain. Okay, so what does Stokes' theorem state? Well, so if I take the exterior derivative of omega, this is a K plus 1 form, right? And we know that, well, a K plus 1 form is something that can integrate against K plus 1 dimensional domains. So we can integrate it against omega, right? That's going to give us a number. We talked about how to integrate differential forms in the previous lecture, so if you need to review that, please just check out that lecture. Okay, so this is a well-defined integral. What is this equal to? What does Stokes' theorem tells us? That it's actually equal to the integral of omega, a K-form, along the boundary of omega. Okay, so omega is a K plus 1 dimensional domain, so its boundary is going to be 1 dimension lower, and so K-dimensional. Okay, so the left-hand side is a K plus 1 dimensional integral, and the right-hand side is a K-dimensional integral. And as we saw in the fundamental theorem of calculus, right, the left-hand side is something that's going on in the interior, whereas the right-hand side is happening on the boundary. Okay, and we have a K plus 1 dimensional integral on the left-hand side, and we have a K dimensional integral on the right-hand side. So pictorially, here is omega, and here is its boundary. Okay, and so we can integrate the differential, the exterior derivative of omega in the interior of omega, and that's related to, or it's equal to, the integral of omega, little omega, on the boundary of big omega. Sorry, there's two omegas here. There's the little omega, that's the differential form, and the big omega, that's the space. So this is Stokes' theorem. And when I said in the introduction that it's simple, that's the sense in which I mean it's simple. It's it involves so few symbols, and it encapsulates in a very compact way something that's actually very useful and very remarkable. And it will become more remarkable once we see how just this very simple statement actually, when you unpack it correctly, implies all the various integral theorems that you've seen in multivariable calculus. Okay, but before we go on to explain how Stokes' theorem can recover the various theorems in multivariable calculus, let's first make a few noteworthy observations that are important for understanding Stokes' theorem correctly. So the first observation to make is that orientations are needed to get signs right. Okay. So we can already see this in the one-dimensional case. Right? So if we have something like this, okay, and now I'll just work with differential form notation. So df is just the derivative of f times dx. So that's exactly the integrand that we see in the fundamental theorem of calculus. Okay, so what we wrote above was that this is equal to f of b minus f a. And if we redraw this interval, what's implicitly happening is that we've oriented the interval from a to b. Right? So here we took b greater than a, and we went from left to right. Right? Because left to right is the positive direction along the real line, and our canonical orientation is to go in the positive direction, and that's how we get this formula. But if we reverse orientations, then we'll pick up a minus sign everywhere, and we can describe it as follows. If we had the leftward orientation, then we'd be integrating from B to A, right? These actually differ by a minus sign, recall. Okay, but if we just ignored the first equality and just don't make any reference to that, how can we intrinsically think about signs and orientations? Well, the right-hand side would just be f of A minus f of B, because now, since the orientation goes to the left, then A is the upper limit and B is the lower limit, and the right-hand side reflects that. But the other way to think about this is that we always, by convention, use the outward normal to orient all our objects, essentially. Well, the boundary, that is. So we can orient the boundary using outward normal. Okay. So in this case, what does that mean? For an interval a to b, the outward normal at A is the green arrow pointing to the left, since that goes away from the interior. And likewise, the outward normal at B is the green arrow pointing to the right. In the first case, when we integrate from A to B, our orientation of the interval is given by the direction from A to B, which we draw as an arrow pointing to the right, circled in blue. Thus, the boundary point at A gets a minus sign, since its outward normal and the interval's orientation are opposite, left versus right, whereas the boundary point B gets a plus sign, since its outward normal has a consistent orientation with the interval. Both point to the right. Right, so that's why we have a plus and minus here. But when we orient in the opposite way, the outward normals at A and B, now shown in orange, are the same as before, since they depend only on the notion of outside and inside and not on the orientation of the interior. But this time, the boundary point A gets a plus sign because its outward normal agrees with the orientation of the interval, and likewise, B this time gets a minus sign. So whenever we do an integral, we have to orient things properly. So back in the general statement here, so we need to have omega needs to have an orientation. And then when we use this outward normal, this induces an orientation on the boundary. So this gets induced orientation on boundary. Okay, and we talked about orientations in lecture 2. So feel free to review that if you want to review how to think about orientations. But we will look at n equals 2 and n equals 3 shortly. So k equals 2 and 3 soon. So if this was pretty abstract, we'll see how orientations work out there. But I hope it's already clear how this works in the one-dimensional case. Basically, you have to choose a direction for your line, and that tells you how to weight the boundary points accordingly, whether they get a plus or minus sign. Okay, so there's quite a bit of proper care of sign management going on in the background in stating Stokes theorem. Okay, so we know that orientations are very important to get the signs right. Another very important thing to observe from Stokes theorem is the following special case. So suppose now we have an empty boundary. Okay, so our domain just doesn't have a boundary, right? Omega could just be, so for example, in the one-dimensional case, omega could just be a closed curve, right? Or it could just be a closed surface, like a sphere. Right? The boundary of the sphere, right? That itself doesn't have a boundary. So if your omega doesn't have a boundary, right, then the right-hand side is just 0. in Stokes theorem, right? We have an integral on the interior is equal to an integral on the boundary. And if this boundary is empty, then that integral is 0. Okay, and that's a very remarkable fact. So in particular, if I'm integrating some k form on some k-dimensional domain that doesn't have boundary, I can add the exterior derivative of any differential form, right? So here, let's just be a little more explicit. So omega is a k form, little omega is a k form. So using omega, sorry, abusive notation. There's omega k, which means degree k forms, and then there's just omega, which is just a domain or a region. This is a k-dimensional. Okay, sorry, I didn't realize that abusive notation, but I hope that's not too confusing. This is a k form, and then alpha is a k minus 1 form, right? So that way, d alpha is a k form. Okay, just making sure that all our types match up, essentially. We're integrating k forms against a k-dimensional space. So based on this fact right here, that if you don't have boundary, that the integral of d of something is 0, that means that if I integrate a form, this omega, little omega over big omega, that integral doesn't change if I add anything that's d of something. And if you go further along this line of thought, what you end up finding yourself with is this concept called cohomology, or more specifically, de Rham cohomology. Okay? So that's an entire subject of study in and of itself, and we don't have time to go into it, but I just thought I'd insert that comment that Stokes theorem is sort of a fundamental part of this entire subject called de Rham cohomology. And it's a very rich subject tying together differential geometry and topology. Okay, so now that we've stated Stokes theorem, let's look at examples and how we can derive and obtain the multivariable calculus theorems that we talked about before from Stokes theorem. So we mentioned before that we have the following three theorems. We have Green's theorem, Stokes theorem from calculus, which will be a special case of the Stokes theorem from differential geometry that we just discussed. And then we have the divergence theorem. Okay, so we're going to see how all three of these are really just special cases of the general Stokes theorem. So let's first start off with Green's theorem, since it's the simplest one, and then we'll work our way up. Okay, so what does Green's theorem state? It states the following. Suppose I have the following integral over a closed contour. So now we're in dimension 2. Okay, so this is a contour in the plane. And so I can do this integral on the left-hand side along the contour, and that's equal to the following integral on the interior, which I'll call d. And what is the integrand? It's going to be that. Okay, so that is what Green's theorem states. Okay, and let's maybe make a few comments. So first is the following. I've implicitly done this already, but I thought I'd just make it explicit. So basically, I won't distinguish between single integral and a multiple integral. Okay, so sometimes you'll see in calculus text that if you're integrating over a curve, it's just a single integral, whereas if you're integrating over a surface, it's two integrals, and if you're integrating over a volume, then it's three integrals. So, this notation doesn't generalize when you're integrating in n dimensions. So, the convention I'm using is just to integrate by writing a single integral sign and just putting the domain in the bottom, right? So we see here that it's only one integral sign, and the fact that d is two-dimensional tells you that it's a two-dimensional integral. So there's no need to write multiple integrals. The only time you write multiple integrals is if it's multiple one-dimensional integrals in succession, and we'll see that later. But in a single integral itself, the domain is just specified by the domain itself. You don't need to use more than one integral sign. Okay, so that's just one notational comment. And now let's return to the issue of orientations that I discussed earlier. So the way we have to orient things is such that C has to be traversed counterclockwise, okay? And we can see that that's consistent with what we discussed earlier. So the reason why C has to be traversed counterclockwise is the following. So we said that we want to orient C using the outward normal, right? So here are some, outward normal vectors, right? So outward in the sense that D is a bounded domain. So the notion of out makes sense. It's what's pointing outside the domain. And we need the orientation of C to be consistent with D when we enhance it with the normal direction. So let's focus, say, on this point right here. So we have this outward normal, right? And if we go counterclockwise, right, we have this orientation. And we see that with that orientation, you're going counterclockwise to go from the first vector to the second, right? So in other words, right, this is a 90 degree counterclockwise rotation. And so if you look at the matrix whose columns are this first vector, I'll call it U1, and then U2, right? That determinant is positive, right? And so that's consistent with the default orientation on R2, right? R2, in two dimensions, we like to orient things by, say, choosing the x direction and then the y direction, right? So the x direction is 1, 0, and the y direction is 0, 1, and then the determinant of that is 1, which is positive, right? So we want to go along the curve in such a way that the second direction gives you a positively oriented orthonormal basis. If you went counterclockwise, you see, if you went this direction, right, minus U2, you'd pick up a minus sign and then you'd be negative, right? And that wouldn't be consistent with the orientation of R2. So as you can see, by requiring that our first basis vector is this outward normal, we have a precise choice about which direction to go along the curve to make a positively oriented basis. We have to go counterclockwise, okay? So that's the sense in which using the outward normal from our domain tells you how to orient the boundary. Okay, so that covers this part. And again, if this was a little confusing, please see lecture 2 to get a review on orientations and the determinant. Okay, so let's look at Green's theorem, and we can see that indeed it really is just Stokes' theorem, right? Because, well, what's the proof? Right? So if I let little omega be f dx plus g dy, then d omega is partial g partial x minus partial f partial y dx wedge dy. Okay, and then Stokes' theorem is just call that's it's this statement, and that indeed is Green's theorem, right? This is the right-hand side of Green's theorem, and this is the left-hand side of Green's theorem, and this is the left-hand side of Green's theorem. Okay, and that's all there is to it. Let's just do a computation so we see how this works. Okay, so let's work with a very simple example. So let's just let D be the unit disk in R2, and then C is its boundary, so it's the unit circle, right? Okay, and then we can consider the following integral. So we're going to have minus y dx plus x dy. Okay, and let's just do that computation, and then we'll also independently compute the right-hand side, and let's check that those agree. Okay, so since we're on the unit circle, right, we're going to parameterize our curve such that, well, our curve, let's call it gamma of t, sweeps out coordinate points here. So this is a pair of points given by gamma t equals xt, yt. And since it's the unit circle, well, we can think of t as the angle that is swept out going counterclockwise. And so this is just cosine of t, sine of t. Right? So we've done these kinds of integrals previously in lecture 3 and lecture 4. So this is in some sense a review. If you want to brush up on that, feel free to check those out in lecture 3 and 4. So I'm sort of kind of going through the computation quickly because we've seen how to do these integrals before. Okay, so we are parameterizing our curve C, right? That's how we do these integrals. And of course, we could think of it as a pullback, but let's not go back into that language. We don't need it for now. We just now can substitute y and x as functions of t and do the integral, right? So t is going to go from 0 to 2 pi, right? Because a full rotation is 2 pi, right? So here t goes from 0 to 2 pi to traverse our circle counterclockwise. And so we have sine of t d dt of cosine of t plus cosine of t d dt sine t dt. Okay, and then that just simplifies to minus sine t minus sine t plus cosine t cosine t. So that just becomes sine squared plus cosine squared, which is identically 1. And so we just get 2 pi. Okay, so that's how we do that contour integral. And if we were to apply Stokes theorem or Green's theorem, right? So we have to compute, well, we can write it in the form that it was stated in Green's theorem, right? So we take the partial derivative of x with respect to the coefficient of y, so the function g, which is in this case x, minus the partial derivative with respect to y of the coefficient of dx, right? Which is again just the exterior derivative of this guy regarded as a 1 form. Okay, and if we just work that out, that's just 1 plus 1. And so it's just now twice the area of the unit disk, which is just, well, the area of the unit disk is pi, so now it's twice pi, and it's 2 pi. So indeed, the answers agree. Okay. All right, so we've just confirmed Green's theorem in this explicit example. And again, Green's theorem is just a very special case of Stokes' theorem. It's Stokes' theorem in 2 dimensions. Okay, so now let's move on to Stokes' theorem, the multivariable calculus version, and see how that's a consequence of the differential geometric Stokes' theorem. Before we do that, though, we have to discuss the concept of curl, because the curl of a vector field is what occurs in multivariable calculus, Stokes' theorem. Okay, so now we're actually specifically in dimension 3, since that's the only dimension in which the notion of the curl of a vector field makes sense. Okay, so let's recall what we mean by the curl. So if I have a vector field V, its curl is, well, it's written as follows. It's the cross product of this nabla operator. This symbol here is what's called nabla, and this x here is the cross product. Okay. Well, let's just write this out explicitly. So we're going to take the determinant of a 3 by 3 matrix, where we're going to put V in the last row, its components with respect to the usual basis vectors for R3, right? So V is that. Nabla is just it's basically just a notational device for keeping track of a bunch of operators. So it's the operator, it's the vector valued operator whose components are just the derivatives in each of the respective directions. Okay, and so the way cross products work, we're just going to place the components of this operator into the second row of this matrix. So this is the operator partial derivative with respect to x1, the partial derivative with respect to x2, and the partial derivative with respect to x3. Okay, we're supposed to get a vector out of this, so we'll just put some basis components here. We'll just use the notation I, j, k just to make everything clean and distinct. So I, j, k are just some conventional notation for the coordinate directions in R3. Right? So these are coordinate directions in R3. Now, in differential geometric notation, we typically would just write partial x1 for I, partial x2 for j, and partial x3 for k. But that's a bit confusing because that notation is overloaded, right? We are already using them as differential operators here, so it would be confusing to also at the same time think of them as tangent vectors. Of course, tangent vectors are directions, but they're also differential operators, as we explained in lecture 3. So for the time being, we can just use notation that disambiguates that usage, right? So I is just the same thing as gdx1, but just thought of as a basis vector, and likewise for j and k. Okay, so now we're going to compute this determinant, and we just use the usual rules of how to compute a determinant. So going along the first row, right, we'll have I times the determinant of the 2 by 2 matrix obtained by removing the column and row containing I. So we compute the determinant of this 2 by 2 block. Right, what do we get? We get that. And then now we go to the j term, we take a minus sign, and we compute a corresponding determinant there. So now we're going to have those two terms. And then finally, the term with k. And when we compute its corresponding coefficient, it's the determinant of the 2 by 2 matrix, right, this 2 by 2 matrix, because we remove the row and column containing k. Then we have okay, so that's what we get. Okay, so that is the curl of V. It's another vector field, and these are the three components, right? The first component, the x direction, the second component, the y direction or the j direction, and the third component, the z or the k direction. Okay, now when you look at this, it actually looks a lot like the exterior derivative, right? It's got derivatives, and you have a very similar looking alternating pattern of signs, and also the way the indices are all occurring, right? So we can look at the first grouping, for example. We have the one direction with I, and then the coefficients involve 2 and 3, so they all involve distinct directions. Likewise, with the second term, we have the second direction with j, and then we have coefficients depending on the 3 and the 1 component, also distinct directions. So this looks a lot like the exterior derivative, and the way we're going to recover the exterior derivative is to make the following observation. Let's contract the curl with the unit volume form on R3, okay, which is dv. So dv always means, well, in Rn, just the product of all the coordinate basis 1 forms, which in our case, since we're in 3 dimensions, is this dx1 wedge dx2 wedge dx3. Okay. And so we can contract the curl of v with dv. The contraction operator was explained in the previous lecture, lecture 4. Okay. So feel free to look at that for a review if you need to do so. But let's just go ahead and do the computation. So the way the contraction works, right, is we're going to, let's see, how are we going to write this out? So the contraction is a linear operation. So let's do 2 steps at once here. So I'm going to rewrite the curl at, okay, so I'm going to replace I now with partial derivative notation. So we're going to contract the first component with dv, and likewise with the other components. Okay. So, oops. Okay, and then finally the third term. Okay. And so we have to evaluate now these 3 terms. Okay, and recall the way contraction works is basically these tangent vectors here are going to pair with each of the components of dv. Okay, and because these are coordinate tangent vectors and coordinate differential forms, the only pairing that is non-vanishing is the pairing between a partial xi with the same dxi. Okay, so in other words, let me just say this very informally, this contraction is going to sort of pair up partial x1 with dx1. This likewise pairs up partial x2 with dx2, and likewise partial x3 with dx3. Okay, And so when we write this out, right, when the partial x1 and dx1 pair up, they cancel, and we get back a 2 form consisting of all the remaining components of dv. So in this case, dx2 which dx3. Okay. Likewise with the second term, the partial x2 pairs with the dx2, but we have to move it past the dx1. So the way this works, you could think of it as dx1 wedge partial x2 contract with dx2 wedge dx3 with a minus sign, because we had to move this one past this dx1. Okay, so whenever you have to move things past one forms, you tangent vectors across one forms, you're going to pick up a minus sign. Okay, and then this just is going to evaluate to 1. Okay, and finally the third term, something similar happens, but you have to move it past an even number of terms, so you don't get a minus sign. So here we would have dx1 dx2 wedge partial x3 contracted with dx3, and this also evaluates to 1. Okay, 2 minus signs gives you a plus sign, so we don't write that. Okay, so let's just finally simplify this. Okay, so let's just group terms together. So we're going to have the dx1 wedge dx2 term, its coefficient is that. We're going to have the dx1 wedge dx3 term, so we have 2 minus signs here. They're going to cancel. And finally, the dx2 wedge dx3 term. All right, and now this is looking like the exterior derivative, right? Because now this is just the exterior derivative of v1 dx1 plus v2 dx2 plus v3 dx3. Okay, and we can just check that. So this is how we can see that the curl, right? So we computed the curl, we contract it with the volume form, and we get back d of something, which is like the original vector field, except that we replaced partial xi with dxi, right? So we took a vector field, replaced tangent vectors with their corresponding coordinate cotangent vectors, and if we take d of that, well, recovers the left-hand side. This is what this computation shows. Let's organize this computation to what's called a commutative diagram. Okay, so what did we just show? So let me use some slightly fancy notation, but it's fairly standard, so it's good to, well, might as well introduce it. So let me not explain the, all the details, but let me use this gamma of t as sort of the space of vector fields. And what this notation reflects is that we can think of vector fields as what, well, in fancy notation and fancy terminology, sections of the tangent bundle. Okay, so gamma is sections, t is tangent bundle. I'm not going to go down the route to explain everything, but I'm just going to use this notation because it's proper and just give a hint as to why that's the case. But okay, so gamma of t is just vector fields, right? The space where v lives. So v lives here, okay? And we defined an operation called curl, which returns you another vector field, right? So to a vector field V, we get the curl of V, and that's another vector field, right, given by this formula here. Okay, so that gives us that arrow curl. And what did we just do? Well, we can contract a vector field with the volume form. And if you contract a tangent vector or a vector field with a three-dimensional form, you get back a degree 2 form. Okay. All right. So that's one part of our commutative diagram. We just showed that the 2 form we got was actually the exterior derivative of something. Okay, so 2 form has to be the exterior derivative of a 1 form. What 1 form? Well, that's what this map is, and let's just call it the dual map. Okay, what is the dual map? The dual map takes a vector field and just converts the coordinate tangent vectors to the corresponding coordinate 1 forms. Okay, so that's what this dual map does. And this is something particular to n-dimensional Euclidean space. It generalizes to more general settings. So for those of you who go on to study more mathematics, the right way to think about this is actually in the setting of Riemannian geometry. So in general, need a Riemannian metric to define the dual map. Okay, it's essentially the inverse of the metric is what allows you to go from tangent vectors to cotangent vectors. Okay, so but this is just you know, kind of side information and further context. We don't have the time to go down the full path for those things, but it's good to know the right context for these things. Okay, so we have this dual map, okay, and that allows us to define this diagram. And now links together all these elements. Okay, so this diagram right here relates curl with the exterior derivative, right? So it links with the exterior derivative, d. Okay, so now with this underway, we can now state the multivariable Stokes theorem and see how it's a simple consequence of the differential geometric Stokes theorem. Okay, so let's do that. Okay, so this is the calculus version. Right, and we are in n equals 3. Okay, so what is the statement of Stokes theorem? So suppose I have a closed contour, okay, which I'll call C. And suppose I have a vector field along it, okay. It could be pointing in various directions, okay, but it's a bunch of tangent vectors all living along the curve C. And the curve C, right, is well, C is parametrized by some function gamma, right? And so when you have this parameterization, you get sort of you get the tangent vector associated to such a curve. In calculus, they call it something like the line element. And what you can do is form all these dot products with this vector field in blue with the line element or the tangent vector. The tangent vector is given by gamma. So the way this is written in calculus notation would be v dot d gamma. Okay, so along the curve, you always have this gamma dot, right? These tangent vectors are going tangent to the curve. And this given vector field v is just some independent vector field, and you could just form their dot product, right? So I should explain what the dot product is, right? So if I have two vectors, so then the dot product is just the coordinate-wise multiplication of the components, right? Then u dot b is just u1, v1, u2, v2, dot, 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 un, vn. So this is the dot product in general n dimension, and we're going to restrict it now to 3 dimensions. Okay, anyways, so you can compute this dot product along the curve. That's going to be the left-hand side of the Stokes theorem. You have this contour integral. What is it going to be equal to? Well, suppose this curve bounds some surface, right? So let me just draw it here in green. So it's a little bit hard to draw, but imagine this surface kind of coming out of the page and bounding this curve, right? And it's going to have a normal direction, right? Everywhere. And again, you have to choose sort of this outward normal direction based on orientations, the orientation that's needed to make Stokes theorem work. So the right-hand side of our theorem is going to be that I can take the curl of v, take its inner product with this normal direction, and then integrate along the surface, right, which has its own area form. Area form just means volume form in dimension 2, and the one associated to the surface. Okay, so here's the surface S in green. All right, so this is the statement of Stokes theorem, the calculus version. Let's recap. Okay, it's saying that to compute this contour integral on the left-hand side, formed out of this vector v, formed out of dot products with v and the line element formed by the contour c, which is parameterized by the curve gamma, right? So you just compute all these dot products and integrate along the curve. It's a one-dimensional integral. That's given by a two-dimensional integral. And that two-dimensional integral is also can be computed as an integral over dot products, where now I compute the curl of my vector v, and it's a new vector field, and I compute the dot product with n. So I form those dot products, and then I integrate over the surface, right? So one thing to note is that, well, there's several things to note here, but you see, once again, it has all the elements we need for Stokes theorem, right? There's sort of, you have an equality of two integrals. One is one lower dimension than the other and formed out of the boundary, right? So this C here is the boundary of S. So we have this sort of boundary aspect going on. We also have a curl is a differential operator. So as before, right, the thing that's being integrated in the higher dimensional space has a derivative on it, and that indeed is what the curl is doing. Okay, and so our job now is to see how this is actually just the differential geometry Stokes theorem in disguise. Okay. Okay, and let's go ahead and do that. So let's prove Stokes theorem by reducing it let's prove the calculus Stokes theorem by reducing it to the differential geometry Stokes theorem. Okay, so first thing to note is that, note that v dot, this integral here, is really just the, well, let me call it, use more succinct notation, is omega of v integrated along c, where omega v is just the dual of v. Okay. Just a comment, when I wrote this left-hand side here, I was using more calculus notation, where in calculus, you don't always think of things as differential forms. You just think of them as maybe functions, and there's a differential form hiding in the background. So this expression here, I think of, I'm using calculus notation where I'm integrating a function, v dot d gamma, along the curve, and I rewrote it in such a way that I should always be thinking of integrating a differential form along a curve. It's sort of like the distinction between the integral of f from a to b versus the integral of a to b f, dx. There's always that sort of a dx in the background, and likewise, there should always be a differential form in the background. So, so that's just to clarify the notation, and it's not hard to see this equality here, right? Basically because of the way that the dual was defined. So let's actually explain that. Right, the dual satisfies, right? So a dual vector is such that when I evaluate it along any tangent vector u, it's the same thing as v dot u. Okay, that immediately just follows from our definition of dual. Okay, so let's just prove that just so that we're all clear. So omega v of u is the same thing as vi dxi evaluated on some tangent vector or some vector field, which I'll denote as u sub j partial xj. And when I evaluate, right, the i's and the j's have to match up because that's the dual basis property. So this is exactly just vi paired with uj, where j has to equal I. So maybe I'll just write it like this, where I equals j. So then that's just vi ui, and that's just indeed the dot product, v and u. Okay? And so this equality follows from the fact that when you integrate a one form over c, you can think of it as, how do I say? So how do we see this blue equality? It's because, as we've explained in a previous lecture, right, we can evaluate these integrals in terms of pullback, right? And so when we pull back along our path gamma, right, so gamma is, say, a path from 0 to 1, it parameterizes c, so this is the pullback. And now this is an ordinary one-dimensional integral. This is none other than, okay, and by this property here, that's just v dot t. Right, but this follows from this proof right here that we just made for that fact. Okay, so the point is that this blue equality just follows from what it means to integrate a one form and what the dual property possesses. Okay, so we've just rewritten this integral in terms of dot products in terms of an integral of a one form. That's just obtained by taking the dual of this vector field V. Okay, so that's the first step. We rewrote the left-hand side of Stokes' theorem in terms of an integral of a 1 form. Okay, and now this is looking good because now we can start, applying Stokes' theorem. So what does Stokes' theorem tell us? So we now have this integral over C. So this is the differential geometry Stokes' theorem. Now, the key is to relate this back to the right-hand side of the calculus Stokes' theorem, and this is where we use the commutative diagram, right? So we have this diagram that we have here. It says that if I take d of the dual, so that's the lower part of the diagram, that's the same as going along the upper branch, right? Because this is d of omega sub v, that's the same thing as curl of v contract with the volume form. Okay, so we can rewrite this as that. And now we just have to see that this is the same thing as curl of v dot n times ds. It's not that hard to see. Actually, I did a computation at the end of lecture 4, which basically illustrates why this is true. And let me just repeat the argument there, right? So if I have some surface, let me just draw it like the upper half sphere, which is the example I did in lecture 4. If I want to, let me back up. If I have a volume form, right? A volume form is just formed out of 3 orthonormal directions, 3 unit directions that are all mutually perpendicular. So I can always take that to be consisting of a normal direction and and 2 that are orthogonal to it, which will form this area form that's tangent to the surface, and therefore it's the area element of the surface. And when I contract the curl of V with the volume form, and I want to look at which components are parallel to S, then the contraction that I ought to care about is the one in the normal direction. Okay. When I integrate along S, I only care about things that are living on S, that are in this case tangent to S. And so I have to sort of peel off the normal direction. And that peeling off is precisely this dot product. Okay. I also do this in a particular example at the end of lecture 4. So you can look there to see how this works out in terms of an explicit computation. But okay, so this is the basic fact we need, that this curl of V contracted with dV, when I restrict it to S, I can rewrite that contraction as the following, as this dot product, weighted by the area form. Okay, and once we have that, then this is exactly what the calculus version of Stokes' theorem is saying, right? So we've just proved what we wanted to, because we've shown that that this is the left-hand side of Stokes' theorem, and this is the right-hand side of Stokes' theorem. Okay, so we've shown now the calculus version. Let's do a just quick computational example. We can actually return back to the example that we just did, right? So in the example we just did, C was the unit circle, right? And V is, let's see, so let me just draw C again, right? V was this tangent vector field. right? So then it's going to be this vector field, okay? And that computation, right, is what we computed last time. It's just the same thing as which we showed to be equal to 2 pi, right, as above. Now let's compute this integral using Stokes theorem. So the easiest surface to pick that bounds this curve C would just be the surface S given by the disk itself. Okay, so let S be the disk, okay? And if S is the disk, then the normal to it is just the, well, the upward normal that's, pointing out of the disk, right? So it's hard to maybe a little bit draw here, but let me just draw a different slice. So actually, let me draw it like this. So here's the XY plane, and then there's the Z direction, and so the normal direction. So normal, that, right? Okay. And once more, you have to get your orientations correct, but I chose it correctly. But it's the one that you have to. It's based on this outward normal understanding of orientations. Okay, and you can check this was the correct direction to use. Okay, so if we use Stokes theorem, and then what we should get is, let's compute the curl of V dot n, and now we're going to integrate along our surface, right, which is just the disk. So this is just the standard dx dy area form on the disk. Okay, so we have to compute the curl of V, right? So curl of V so we have a minus y here, and x there, and a 0 there. And we can see that the only component that survives is the k component. Yeah. So only this 2 by 2 block will be non-zero. If you look at any other component, it's going to be 0, right? If you look at the ith component, right, you have this ddx of 0, that's 0. Oops, sorry. If you look at the component of I, right, let me draw it slightly differently, right? You have these two pairings, and then you have ddy of 0, which is 0, and then ddz of x, which is 0, because x doesn't depend on z. Okay, so the I component is 0. Likewise, the j component is 0. Only the k component survives. So you're going to have a k partial x of x minus partial y minus y, and that's going to be 2, right? So this is 1. That's minus 1 minus 1 is 1, and then you get 2k. Okay, or in other words, this is also 2 partial z. Okay, and so this is now 2 partial z dot partial z. And that's just now 2 dx dy. And indeed, it's just 2 pi, because pi is the area of the disk. Okay, and we get agreement, right, as we expected. What's cool about Stokes theorem is that we could have chosen any surface which bounds this contour, right? So we could have chosen a much more difficult contour, like that, some irregular contour. It's going to have its own normal vector field. And nevertheless, whatever that complicated integral is, it evaluates to this answer 2 pi, because it only depends on what's going on along the boundary. Okay, so it's a remarkable reduction in complexity. You can have a very complicated integral along a surface, but if it's of a particular type, if it's a curl of a vector field dotted with a with the normal direction, then you can greatly simplify your calculation by just looking at what that vector field is doing along the boundary, the contour C. Okay, so that wraps up the Stokes theorem, the calculus version, and how it can be obtained from the differential geometry Stokes theorem. Okay, and the last theorem we'll be looking at is the divergence theorem. So the divergence theorem actually holds in general dimension, but let's just focus for to n equals 3 for specificity, but everything we'll be discussing holds in general dimension. Okay, so what is the divergence theorem? Let me first define the divergence operator. Okay, so if V is a vector field, then its divergence is a function, and we can write it in terms of the nabla operator we introduced last time using a dot product. Okay, so that means that right, so nabla was this vector of operations, and if we take the dot product, then that just means we will differentiate each component of VI with respect to the corresponding coordinate direction, right? So this would be in dimension 3, the following function. Okay, so that's the divergence operator. Pretty straightforward. Okay, so it takes vector fields to functions. Okay, what's the divergence theorem state? It states the following. Suppose I have a closed surface bounding a volume V, right? So here's surface S, and the interior is what's I'm calling V here. Okay. Then, well, we can form a surface integral formed out of taking our vector field V, dot prodding it with the outward normal n, and integrating along the surface, right? So now n is the outward normal. We can also evaluate this surface integral in terms of a volume integral. What is that? It will be the divergence of V integrated along the volume. Okay, so that is the divergence theorem. Right? We have an integral along a boundary S, and it's equal to an integral along the interior in terms of a certain kind of derivative, right? In this case, the divergence operator. Okay, how are we going to prove this? And as before, we have to just make the right observations to see how we can invoke the differential geometric Stokes theorem. Okay, so we're going to have another commutative diagram in this case. Okay, so we have our space of vector fields, this gamma of t. We have the divergence operator, which maps vector fields to functions. I'll just call that omega of 0. Okay, in order to get something that we can integrate, we need to multiply by a volume form. So I'll just call it dv. It's also contraction, but when you contract a function, it's just multiplication. So we're just going to multiply by the standard volume form. So this is dx1 through dxn. And that's going to give us an n form, the top form that we can integrate. Okay. Okay. Well, we want the exterior derivative to occur here. So let's just put our exterior derivative. We know it has to, the domain has to be n minus 1 forms to map to n forms. How are we going to make this map? Well, the only thing that makes sense is going to be just to contract with the volume form, right? It's essentially the only natural way we're going to go from vector fields to n minus 1 forms. Okay, let's check that this is true. So let's check this direction, right? If we contract and then do the exterior derivative, let's check that that's the same thing as computing the divergence and then multiplying by the volume form. So let's do d of little v contract with the volume form. Okay, so then that's for n equals 3, it's going to be d of v1 partial x1 plus v2 partial x2 v3 partial x3 contracted with dx1 dx2 which dx3. So we have d of v1. The partial x1 will cancel off the dx1 and give a dx2 x3. The partial x2 will cancel the dx2 but pick up a minus sign. So that's minus v2 dx1 wedge dx3. And finally, the partial x3 will cancel out the dx3 and pick up two minus signs, so an overall plus sign. Okay, and then now we take the exterior derivative and we see that we're going to get a coefficient that is exactly the divergence, right? Because we get this. Oops, forgot to put a wedge there. And then we're going to get and then finally the last term. Oops, forgot to put a wedge here as well. Okay. And then now we just rearrange the terms so that everything is a dx1, dx2, dx3, right? So we have to move the 2 past the 1 here and the 3 past the 1, 2, 3 there. We're going to get a minus sign in this case and no minus sign in the second case here. Again, because of odd and even permutations. So altogether, we're going to get that as our coefficient in front of dx1, dx2, dx3. And indeed, we see that that is the divergence of v times dv. Okay, so we've just shown the commutative diagram. That is, if we go along the down and left, that's the same as moving to the right and down. Okay, so with this, now we can reduce the divergence theorem to the general Stokes theorem. Okay, so how are we going to do that? Right, so we now have this integral. We've explained before that this is the same thing as v contracted with the volume form integrated along S. Okay, so that was explained also in our proof of the calculus Stokes theorem. Now, this applying the general Stokes theorem, we can compute this as d of this differential form, and now compute it along compute it over the volume on the interior, right? So this was a 2 form, and when we take the d of it, this is now a 3 form. Okay, and based on our commutative diagram above, we know that contracting and then applying d is the same thing as computing the divergence and then multiplying by the volume form. So this is the same thing as the divergence of v times the volume form. Okay, and that's exactly Stokes' theorem, right? Because now the divergence theorem, because now we've equated this, the left-hand side of the divergence theorem, with the right-hand side, right? That's the proof. All right, let's just do a computational example just to see how this works. Okay, so here's an example. Suppose we have a cylinder. The boundary of the cylinder is our surface S, and the volume is the interior region. Okay, so this cylinder has height h, and this is these disk faces are just the unit disk, right? Radius 1. Okay, so capital V is the interior region, and then we're going to have our vector field be just the vector field x partial partial x. Okay, so in other words, it so if so here we have the upward is the z direction, x is that direction, y is into the plane. Then our vector field v looks something like this, right? It's positive there, negative there, and let me do a bird's eye view. So if you do a bird's eye view, where this is x and y, then our vector field looks something like this, right? Okay. So the reason why this is called the divergence theorem is because it has an interpretation in terms of flux, in terms of how much stuff is flowing out of the surface. And as you can see, based on this picture, if you imagine blue as water, it looks like this is basically a source vector field, right? There's a net flow of water out of this this interior region here, right? So there's this net flow, and the divergence is going to having a non-zero divergence is going to reflect that. Okay, so anyways, so that's just sort of the physical interpretation of this theorem. Okay, so let's actually just do the computation. What is this surface integral? So we're going to have v dot n ds along the surface S. So let's see. I should write the cylinder as sort of the, how would I write this? As sort of the d top union, I don't know, I'll call it a roll, like as if it were a toilet paper roll, right? And then d bottom. Okay, so there's the d top, d bottom, and then the other part is the roll, right? So first thing to observe is that this integral only gets contribution from the roll part. Why is that? It's because the top and bottom, right, the outward normal is in the z direction, and that's orthogonal to the vector field v, right? So on d top and d bottom, n is equal to plus or minus partial z, and that's orthogonal. In other words, it has zero dot product with v. Right, so we can ignore that. We just look at the roll part. And for the roll part, well, it's translation invariant in the z direction, so we can just factor that out. We have the 0 to h dz, and then we just have an S1 part, circular part, right? So the roll, the roll region, right, is just 0 to h cross S1. And along S1, we now just compute v dot n, okay, where this n, right, this n here is just this outward normal here. Okay, so n, if you think about it, is just x partial x plus y partial y, right? Because it just radially points outward. In our polar coordinates lecture, in lecture 3, we saw that this was indeed just the radial vector field, right? This is just partial r, essentially. Okay. And since v, let me write this, right? Since v is this vector, right? The only term that gets a contribution to the dot product is this term. So what we have now is v dot n. That's just x times x, right? So let's just write that. So only this term survives. And we get x squared integrated along the circle, so we can write that as x squared as a function of theta. Yeah, let's call it theta, d theta. Okay, and this is, of course, just cosine squared of theta, d theta, right? Because if we parameterize our circle, then that's just cosine theta, sine theta. Okay, and then we can easily do this integral, right? The first integral is just an h, and the second one you can just check is just pi. So pi h is our answer for this integral. All right, and let's finally compute the right-hand side of the divergence theorem. We have to compute this integral over the volume in the interior of the cylinder, the divergence of v over the volume form. Okay, and well, remember that v, which is x partial x. So we have well, partial x and nothing else. There are no other components. And then we have the volume form on the cylinder. So really that's just the, well, it's just dx, dy, dz, where x and y are now, well, let's just write it like this, right, over the volume form. And now, well, ddx of x is just 1, and then we have a dx dy, which we could think of as an area over the disk, and then a dz from 0 to h for the cylinder, right? Right, so since we're now looking at the volume, right, there's a disk, a solid disk, and then to compute the volume, it's just the area of the disk times the height h. Right, and the integrand is 1, so it indeed is just the volume. Right, I chose this vector field v to be especially simple, so I don't have to do any more work. Okay, well, the area of a disk of a unit disk is just pi. And then I do the last integral, I just get h pi. So indeed, two answers agree. Okay, so this confirms the divergence theorem in this particular example. Okay, so let's just summarize what we did in today's lecture. Okay, so what we did was we introduced Stokes' theorem in its most general differential forms version. Right? And it could be described very succinctly. It's just integral of an exterior derivative in a region is just the integral of that differential form along the boundary. And we saw that the familiar calculus theorems, there are several of them, were actually just special cases of this more general and powerful theorem. Right? So we have Green's theorem, we have the Stokes theorem calculus version. This was true for n equals 3. Yeah, maybe it's also helpful to think of, let's see, if omega is a k form, right? So then here's k equals 1, k equals 1, and then we have the divergence theorem, which actually holds for any n, so we could just say k equals to n minus 1, but in calculus you'll see n equals 3 in calculus. Okay, so that's what we just saw in this lecture, how we can obtain these three theorems out of one sort of master theorem from differential geometry. So if anything, this was quite a technical lecture, but I hope it sort of illustrates some of the beauty and power of differential forms and differential geometry in general. So I didn't prove Stokes' theorem, but of course you can find that in any textbook, and it's actually not that hard to prove it, at least at a heuristic level. If you sort of think about it, it's really just a repeated application of the fundamental theorem of calculus. So if your region is a cube, so maybe I'll just leave that as an exercise. So exercise, let omega be a cube, and then you can prove Stokes' theorem using repeated fundamental theorem of calculus in each direction. Right? So for example, for n equals 2, right? Here's your unit square. You can orient it, the boundary in this counterclockwise fashion, and when you apply the fundamental theorem of calculus, you can apply it in the x direction. So in the x direction, you'll get boundary terms corresponding to constant x values. And if you apply the fundamental theorem of calculus in the y directions, then you'll get contributions corresponding to these two terms, which gives you the boundary. Okay, so I'll just leave that as an exercise. It's not too hard, mostly getting the signs right. And you'll see exactly how all the signs actually conspire to give you the right answer. Okay, so it's actually a pretty good and instructive exercise in how and why signs are so important. Okay, so I thought this was a very beautiful piece of mathematics that's worth knowing if you want to sort of maybe have some justification for why it's worth studying differential forms and differential geometry more generally. But also I wanted to introduce Stokes' theorem because then it gives us some tools by which to understand curvature, which of course is very important in studying not only Riemannian geometry, but also gauge theory. And so we'll look at curvature next time. Okay, so I hope this lecture was informative, and I will see you all in the next lecture.